In week 1 of our robotics theory videos, we introduced the idea of coordinate frames. Most robotic systems have to deal with many coordinate frames. Some are attached to specific parts of the robot, such as sensors or actuators. Others represent key locations in the world around our robot. And to complicate things further, many of these frames move over time, and we want to make sure we're using the correct relative transforms for the time our data was collected. The TF system, used throughout ROS, gives us a solution for keeping track of our system's coordinate frames. This system is built around the TF2 library, along with a collection of packages that provide integration helpers between this library and other parts of ROS. TF represents our collection of coordinate frames as a tree. Each node in the tree is a named coordinate frame. The edges between nodes represent the transforms between the two frames the edge connects. Because it's a tree, each frame has a single parent frame. The child frame's position is defined relative to that of the parent frame. Here's what a TF tree might look like for a robot in ROS. At the root, we have our global reference frame, often called map. Following the tree down, we see the ODOM and baselink frames. From there, the tree branches out into all of the different frames on our robot. The structure and names in this tree are based on the conventions established in Rep 105. This document lays out conventions for coordinate frames in mobile robots. Adhering to these conventions isn't required, but it makes it easier to use some ROS tools and for developers from other ROS-based projects to understand the structure of your system. An important aspect of the TF system is that it's distributed. There is no central program or node that keeps track of the full TF tree. Every node that wants to use data from TF is responsible for keeping track of its own copy of the TF tree based on messages published on two topics, TF and TF static. Each message sent over these topics includes an array of transforms. Each transform connects two frames in the tree. By listening to all of the messages that come across these topics, a node can gradually build up a complete picture of the entire tree. Let's take a look at the TF tree of the robot we use in our programming projects. I'll start up the simulator and use a second terminal to run some tools that come with TF2. The TF2 tools package gives us one program that generates a visualization of our TF tree. We can run this tool with the command ROS2 run TF2 tools viewframes.py. Because we're using a simulator, we'll need to tell it to use simulation time. It will listen to the TF topics for a few seconds and then generate a PDF showing the complete TF tree. This visualization shows us the whole TF tree. The arrow edges point from parent nodes to child nodes. Each edge shows information about the transform between those frames. The transforms with the buffer length 0 are static transforms. The relationship between those frames doesn't change over time. The other transforms are dynamic, and it shows us the frequency the transform data is being published at. While this full tree view is useful to see the structure of our TF tree and check if any frames are missing, we're often more interested in tracking the actual transform between two frames over time. For that, we can use the TF2 echo tool provided by the TF2 ROS package. This command shows us the translation and rotation between the specified frames. The TF2 ROS package also gives us the static transform broadcaster. This tool starts up a node that adds a static transform to the TF tree. One way to use this node is to provide a stand-in transform that would normally be provided by another node. In our projects, we've been using the static transform broadcaster as a fake localization node that always just broadcasts the identity transform between the map and ODOM frames. Here's what starting that node by hand looks like. We give it the XYZ translation offsets, and then the roll, pitch, yaw, angular offsets, and then the parent frame and the child frame. This completely represents the extra transform link that this publisher will add to our TF tree. If we run this command, and then rerun our View Frames tool to take a look at our new tree, we can open the PDF it generates and see that there is now a new frame called map with a static transform to the ODOM frame. The final TF-related tool we'll talk about today is actually RViz. RViz can render the TF tree as a collection of axes with arrows showing the parent-child relationships. To show our TF tree, we can add a new TF display. We'll click the Add button, scroll down by type to TF, and hit OK. Each axis in the 3D viewport is a TF frame. The yellow and pink arrows connecting the axes show us the parent-child relationships between the coordinate frames, with the arrow pointing from the child to the parent. In the display settings, you can toggle on showing frame names, change the size of the markers, and even control which frames show up in the viewport. RViz is probably the most useful tool for actually visualizing our TF tree, since we can directly see the 3D relationship between frames. And that's the fundamentals of what the TF system can do. In the next two videos, we'll see how to broadcast and use TF data in C++ nodes.